Okay, so we've seen that the EM algorithm for Gaussian mixtures consists of two steps. One is the assignment step, where we basically, for each data point, we figure out how much it contributes to the kth cluster. And then there's an update step, where we update the means, the covariances, and the component probabilities. So that's basically what we got from the applying the EM algorithm to Gaussian mixtures and taking the hidden variables to be the one-hot encoding of where each data point, which component each data point came from, right? So you should go back and look at that video if you don't remember what's going on there. So what happens in high dimensions is that the estimation of the covariance it becomes a blocker, right? Becomes a very complex things, because here remember what you were doing was pk given xi, and then xi minus mk, xi minus mk transpose. You're taking these outer products sort of to get like d by d matrices, summing this over all the points, and of course dividing by the number of effective points, which is just the sum of these weights, the assignment weights, right? And this part is what gets computationally complex. And what we're going to show here is that by relaxing the relaxing the goal of trying to model the covariance based on data, by sort of giving up on it, we get the so-called soft K-means algorithm, and then by specializing further, we get the K-means algorithm. So basically, this would be a different route to come to the K-means algorithm. Originally, we were saying K-means minimizes the distortion, and this would be saying that K-means would be a special case of Gaussian mixture modeling in some limiting regime and with some relaxed conditions. So soft K-means, what does it do? It basically, give up on the covariance. Give up on this. Just assume some form of the covariance. Assume that all the covariances are white. So basically, they're the identity matrix times some scaling factor. The scaling factor is the variance per dimension, or the precision, 1 over the precision, right? So this is my nominal precision. I'll just assume it is something, right? And what does that mean? That it means that under the component k, my density looks like exponential minus if the ith chi is assigned to component k, its density would look like this, multiplied by the precision divided by 2. But instead of that, we often assign a term that we call the temperature, and we'll see what relevance that has. Basically, what does that mean? I'm saying that I'm just thinking of the temperature as 2 over the precision. I'm setting it that way, and I'm saying that the probability of xi given k is proportional to this. So I have given up on actually estimating the covariance from the data, and I'm assuming that I'm going to allow some variations around the means. And that how much variation I allow depends on the temperature. I mean, the temperature is just you would have had a 2 sigma squared term here. The temperature is just 2 sigma squared, but there's a particular interpretation that we'll talk about of this temperature as when we talk about deterministic annealing. So I'm going to introduce this term here. So that's our model for the conditional densities. So what does the update step, let's talk about both the assignment and the update steps. So the assignment step, which is actually the one that changes more, both of them change. The assignment step, remember, was computing, using Bayes' rule, the probability of component k given for the data point xi, and so it was pi k p of xi given k divided by p of xi, and remember that we have to, this normalization factor at the bottom is just the sum of terms like the numerator, right? So basically it's summation j going from all the components pi j p of xi given j, right? So any common factors like 1 over 2 pi to the d over 2, etc. will cancel out in the numerator and denominator, and so it's easy to check that this guy specializes now to, because I'm not having the covariance anymore, e to the minus xi minus mk square over 2 times the temperature. That is just plugging in this guy for that term, right? And then at the bottom I'll have j equals 1 to k pi j, the same kind of term, and all the other common factors cancel out in the numerator and denominator, x minus mj square over 2t. So that's the assignment step. So I no longer have to do a covariance inversion to compute the exponential term in the density, right? We don't have to do that. It's just look at the distance squared from the cluster center and divide by I'm sorry, this should not be 2t according to my notation. The 2 should not be there, right? The way I have defined temperature, right? Okay, and the m step is the same as before, except I no longer have to update the covariance. My cluster center is updated the same way as before. Sum over all the data points. What's the fraction of the data point you have assigned to the kth cluster times that data point, and you divide by the sum of these weights, which we have noted already can be thought of as what's the effective number of data points you have associated with cluster K. And we also, of course, have to update the component probabilities, which are just this sum of these weights, P of K given xi, these assignment probabilities, divided by n. Basically, it's the effective number of points assigned to cluster K divided by n. So everything simplifies, and of course, you've given up on modeling the covariance. So that's the soft k-means algorithm, just a simplification of the EM algorithm where we stop modeling the covariance. How do we get k-means from this? Well, if you look at the assignment probabilities and let the temperature go to 0. What happens when you let the temperature go to 0? All these exponential terms, they are going to, they're sort of blowing up. Xi minus mk squared over t is blowing up, right? And so e to the minus of that term is going to 0, but they're going to 0 at different rates. The one that is going to 0 the slowest is the one for which this term is the smallest. So basically let me just make some definitions. So let me say that K star for the ith guy is the, just minimize over the cluster centers, just like you do in k-means, and because we are actually going to get k-means now. You minimize over all the cluster centers, the distance of the ith point, and you take the cluster that is the that corresponds to this minimum. And then if I look at e to the minus xi minus mk square over t divided by e to the minus xi minus mk star square over t, you can see that because this term is bigger for k different from k star, this term is going to 0 faster than the bottom term, right? This exponential is going to 0 faster than this term. So this basically goes to 0 as t goes to 0. So what happens in the limit as the temperature goes to 0, your p k given I tends to 1 if k is arg min over all the clusters, this xi minus mj squared, and 0 else. So we basically recover exactly the k-means algorithm, right? Basically, so this is k-means. You assign to the closest cluster center, and then you update as you were doing before in k-means, right? You basically, what will happen in the update step, remember that the pk given xi's are now just 0 or 1, and so if ck is the set of, just like before, right? If ck is a set of all training points that are assigned to so k is the arg min over j x minus mj squared, exactly like in k-means. Your mk, which was summation I equals 1 to n in the soft k-means algorithm, this over summation I equals 1 to n pk given xi, you simply have that I'm just summing over the i's that have been mapped to ck, the xi, divided by the number of points in ck, just like we had before in k-means. And similarly for pi k, it's clear, right? Pi k is it's going to be I'm going to write it down, but it really doesn't mean much here. It's just the number of points in the kth cluster divided by n. But I'm not really using pi k anymore because I'm not doing these Bayes rule computations in the assignment step. I'm just picking the closest cluster center and mapping the point to that, right? So what we have seen is that by simplifying the Gaussian mixture estimation problem, so we don't estimate covariance, we get soft k-means, and then by specializing it as sort of letting t go to 0, meaning letting the allowable variation around the mean sort of go to 0, I get the k-means algorithm. What's the other thing we can conclude from that? Well, by making the covariances look white, right? I'm basically saying covariance is 1 over beta times I, right? So it's basically t over 2 times I. By making the covariances white in my model, I'm basically saying I can fit basically spherical clusters to the data. So if the cluster has an odd shape, then I'll have a harder time fitting it. Unless it's so far away from the other clusters that I don't have a choice, I'll just map even the odd shapes to the cluster center I have. So let me just give an example. If I have an odd shape like this of data points, bunch of data points here, and another odd shape like that, a bunch of data points here, well, and I give you two clusters, well, you might map them like this and you would be happy. But now if I have a different example, and this is there in the handout in a nicer form, if I have two odd shapes like that are close together, then because I'm modeling spherical clusters, I might group them like this together, which is not what this is 2D, so even the human eye will be able to see this, but that's not what we want really. So these two might have been generated from Gaussian mixtures with two of these elliptical covariance structures, and you are now modeling them as two spherical guys, and you might have a not too many data points in the middle, but you don't really care because your cost function that you're optimizing is better off doing this than that. So it's not that the k-means algorithm or the soft k-means algorithm is going wrong. It's just that it's doing something that it's supposed to do. It's supposed to put spherical covariances model, fit those to the data, and has less room to accommodate odd shapes.